Here I'm going to go through 4 different ways to find enthalpy. And at the end I'm going to go through and kind of try and explain what this is exactly. So something that's a little tricky. But first we're just going to go through, in problem solving, what are the 4 different ways that are commonly seen to find enthalpy. So this is the first way. And this one is one that you would typically see in a lab setting. So if you're doing an experiment to find enthalpy, this is something you'd use. The end result that we're going to get to is that the enthalpy of a chemical change or a physical change for a particular chemical can be determined by how much energy is released in the form of heat divided by the number of moles of chemicals that react or were participating in whatever change was taking place. So in this particular one we have something being burned inside of a bomb calorimeter. And so the energy released from that particular reaction goes to 2 places. One is into the water in the calorimeter, and the other is into the actual container itself, the calorimeter. And so we're going to go through and I'm going to calculate those 2. Now if you're in a regular chemistry class, you're probably only going to be expected to look at water. You're probably not going to do a heat capacity. This is probably a little more for the level of an AP Chem or IB Chem or maybe a college class. But we're going to go through and do the whole thing. And we're going to end up with how much energy was released from this chemical reaction when I did the reaction. So first of all, we're going to do the energy that went into the calorimeter, to get that kind of out of the way. And it says it gives us a heat capacity for the calorimeter, which is great, because that heat capacity is how much kilojoules it takes to heat up the calorimeter by 1 degree. And it gives us our temperature change. So if it takes this much to go up 1 degree, to go up 8.2 degrees will take that much more of it. So 6.8 kilojoules per degree Celsius times 8.2 degrees Celsius for our temperature change gives us how much energy goes into the calorimeter, and that ends up being 55.8 kilojoules. For the water, and this is a problem that you're probably more likely to see. Here we're looking at what I call an MCAT calculation, where we're doing the Q equals MC delta T, where C is our specific heat capacity. So they're never going to tell you the specific heat of water, they're going to assume you know it, but they do give us the mass here as 700 grams. And the specific heat capacity of water is 4.18 or 4.184, depending where you are, maybe 4.186, depending on what your pressure is. I'm going to use 4.184, and my temperature change is the same as it was before. It's 8.2 degrees, they both go up the same temperature change. So calculating that out comes out to be 24,000, I believe. Yep. And I'm going to make that into kilojoules by making that 24 kilojoules instead of 24,000 joules. So what I found here is I found how much energy from my reaction went into my calorimeter and how much of it went into the water in the calorimeter, which means that my total for that then is the sum of those 2, which would be 79.8 kilojoules. Okay. So now I have a much simpler problem. To find enthalpy, all I need to do is take how much energy was released from my reaction and divide that by the number of moles of chemical that were reacted. So I have 79.8 kilojoules, and I had 2.31 moles of chemical burned. So all I have to do is divide those 2, and we end up looking at 34.5 kilojoules per mole. Now at the very end of your enthalpy problems you should do something, especially for a problem like this, you should figure out whether the sign should be negative or positive. And we want to be really kind of clear here. The enthalpy is always going to associate with the chemicals that you're looking at. So we're looking at the energy of the chemicals, are they increasing or decreasing? And we're going to see those effects through other things. So in this case the water and the calorimeter pick up energy, which means that the chemicals in the reaction are losing that energy. And if they're losing that energy, that means that this should have a negative sign with it. So our enthalpy would be negative 34.5 kilojoules per mole. It is much easier to do the negative and positive determination at the very end of the problem as opposed to in the inner workings of the middle. It can be very sloppy. And so it's best to just sit there, get a final answer that's a number, and then sit down and say, okay, should this be a positive or negative? So the first way to find enthalpy is you find a Q through some kind of MCAT calculation or given, and you divide that by the number of moles of chemical reacting, and that will give you an enthalpy. The second way to find enthalpies is using what are called heat of formations. or enthalpies of formations. Okay, so the symbol for this looks like this, not to be confused with the enthalpy of fusion, which involves melting or freezing. Okay, so this is how much enthalpy change is required in order to make a chemical from its elements under normal conditions. Okay, so the definition of this is actually a pretty common question. So if I pick a chemical here, so I'm going to do this reaction down here. So I'm going to pick methane as a gas. So what the enthalpy of formation value for methane of a gas is it is how much enthalpy change there is when I make this from the elements that comprise it. So I'm going to take carbon, which is normally a solid, and we can even get more specific, it's normally graphite under normal conditions. And we're going to take hydrogen, which is normally diatomic and a gas. And so if we run this reaction and form this, the enthalpy change in that is what this enthalpy of formation is. And what's nice about this is that then we get some scientists to go through and make a list of what the enthalpy of formations of all these chemicals are. And then what you can do with their list is you can use them to figure out the enthalpy of a reaction you don't know. Now, a couple important things. One is that means that enthalpy of formation is going to be 0 for any element in its typical standard form under standard conditions. So if I want to make solid carbon from solid carbon, it doesn't take any enthalpy change. And so that would be an enthalpy formation of 0. Okay? And then of course for a compound, it would be from those elements that you would compose it to be able to figure out this value. Alright, so let's go ahead and take a look at one of those worksheets. So we can kind of come up with our values here. And keep in mind that what we're doing is we're going to go through and do methane. So we're looking at methane burning. And so here we have our sheet that has the different values on it. There. Okay. So if we go through, methane here is our first chemical, and it has an enthalpy of formation of negative 74.86. That's going to react with oxygen, which unsurprisingly is an element in its normal conditions would be 0. And then we're going to form two things. We're going to form steam, water, and we are going to form CO2. So from these predetermined values, some other scientists went through and did the previous method of finding these enthalpies using an MCAT problem or a bomb calorimeter, and then they've set them out for us to come through and use. Okay, so let's go back to the other slide now, and we'll show how to use these values. Okay. So what you're going to do with them is you're going to add them up. So we're looking for an enthalpy of a reaction. That's going to be equal to the sum of all the enthalpy of formations of all of my products minus the sum of all the enthalpy of formation of my reactants. So for this reaction down here, all I need to do is take that value for CO2 that I found in the chart, the value I had for steam that I found in the chart, double, and then add those together, and then add together the value for methane and the zeros for oxygen, and then subtract products minus reactants. So if we go through and do that then, the CO2's value is negative 393.5 kilojoules per mole, and the steam was negative 241.8, and I had two of those. Okay, so the fact that you have two of those means it'll take twice as much or release twice as much energy. So you do have to account for the coefficients in the balanced reaction. Okay, so that is the sum of all of my products. Then I want to sum all of my reactants. I have methane, and that was negative 74.8. And then the oxygen is an element in its normal conditions. That's going to be 0. And it's two zeros, but, still 0. So this is the sum of all of my reactants. So then all I have to do is take this quantity, subtract this quantity, and that will then give me my enthalpy for reaction. So for this one, that ends up being a negative 802.3 kilojoules per mole. Now at that point we can go through and analyze that a little bit. The negative here is implying that this is an exothermic reaction, which of course makes sense for combustion, that would be exothermic. We're releasing energy to the surroundings. So this mixture of chemicals loses energy in the process of reacting, and then if you have that happen near you, you'll feel warm. Okay? And then this would be our second method of finding enthalpy. Third method of finding enthalpy is called Hess's law, okay, named after the very famous scientist Mr. Law. And Hess's law is kind of a fun puzzle game. And here's what you have. You have multiple reactions, but one of them is kind of your unknown enthalpy reaction. So I have this reaction up here, and for some reason I don't know the enthalpy for it. And there are many reasons. Maybe it's slow, maybe one of the chemicals is really dangerous, maybe one of them is really expensive, maybe it's really unstable and it's hard to keep as a reactant. So for some reason or another, I don't know what the enthalpy for this particular reaction is. But I do have three other reactions that I have figured out the enthalpy for, somehow, some way. What you're going to do is you're going to take those three reactions, 1, 2, and 3, and you're going to manipulate them to make them add up to the unknown reaction. When you do those manipulations, you will end up changing their enthalpies. But however you change them, when you're done, if you add those new changed values up, they will add up to the enthalpy of this reaction. Now there are two common changes that you can make. So if you have A to B, and that's a negative 20 kilojoule enthalpy. If you reverse the reaction, B to A, that'll flip the sign, okay, which makes sense. You're now making and breaking the opposite bonds. If you have 2A go to 2B or some other multiple, you will multiply that value by that amount. So now I'll do twice as much chemical, I'll get twice as much energy. Okay, so let's go through. And what I like to do on these is I like to kind of circle each reactant and then find it. So I have carbon disulfide, I have that here. So this one, it's in the wrong spot. So it's not important where they are in regards to pluses, but it is important which side of the reaction arrow they're on. So I have a product, I need it to be a reactant. So I'm going to take reaction 3, and I'm going to reverse it. I'm going to put CS2 here, and have that turn into carbon and 2 sulfurs. Now when I reverse that, that's going to take this value, and it's going to flip the sign. So this is now going to be negative 87.9, instead of positive 87.9. Okay. The O2s I have in both these reactions, so I would skip that till later. I would go to the next chemical. CO2 is my next one. That's in this reaction, reaction 1. And it is just dandy as written. So I'm just going to copy reaction 1. Carbon turns into carbon plus O2. Let's see if I can space that out a little better. Carbon plus O2 yields CO2. And I haven't changed anything, so I'm going to end up with this value. And if you're paying close attention, you will notice that this is regular carbon, regular oxygen. Those are elements. That is the enthalpy of formation of CO2 that we saw in the previous problem. All right, the last bit then, I need 2 SO2s. Okay, so before we look at our O2s. Now this has SO2. It's in the right spot, but I only have 1. So I'm going to take reaction 2 and I'm going to double it. Okay, so I want my SO2, and I'm going to do 2 sulfurs plus 2 O2s yields 2 SO2s. Okay, and because I doubled that, I'm going to double this value here. So instead of negative 60, it's going to be negative 120.6. All right, now let's take a little analysis time here. So I have my carbon disulfide here. I have my CO2 here, my SO2 here. Okay. I also have an O2 and then 2 O2s. That's 3 O2s, which is what I'm looking for. So that's now good. And then the other things I have, so when I combine these reactions, I'll end up with the reactants and products I need. But the carbon here and the carbon here, I have a carbon before and after the reaction, so therefore nothing changes with that. And I have 2 sulfurs to start and end, so nothing will change with those. So I can cancel those out to a degree. So what I've done is if I add the reverse of reaction 3, 1 as is, and double reaction 2, I end up with my unknown reaction. Which means if I add this value, and this value together, I get my enthalpy for that reaction. So the delta H for this is then going to be the sum of those, which ends up being negative 602 kilojoules per mole, of course. Okay? So Hess's law is the third way that we can find enthalpy. And this one's more of like a kind of fun puzzle to get everything to work. You just need to make sure that you end up with all the reactants and products you need, and that you end up canceling out all the things that you don't need. The fourth method is using bond enthalpy. So if you're in a chemistry class, you're probably not going to do this. But if you're in an AP class or in an IB class or a college class, you're going to see this. This one's challenging because here you're going to have to go through and you're going to have to figure out what you're breaking apart and making. Okay? So in this particular one, we have ethene to start. So this. And we're adding water. I'm going to kind of draw out all the bonds here. And then those two turn into ethanol. So the important part for this is that anytime you break a bond, that requires energy of you. For the enthalpies for those, that's going to be positive. If you make a new bond, if you form a new bond, then the enthalpies for those are going to be negative. So what you're going to do is you're going to figure out every single bond that you break, and you're going to figure out every single bond that you make. All the breaking of bonds will be positive, all of the making will be negatives, and you're going to add the two together. Okay? Now, how you break and make things can be, depending on the level you want to get into, you might do less or more. So for instance, one of the things I could do is I could just break every single bond on here and make every single bond on here. And that would work. I would get the right answer. But I'm going to go through and I'm going to do a little bit less than that. I'm going to go ahead and break the carbon-carbon double bond. I'm going to break the carbon-hydrogen. No, not that one. Whoops. Whoops. I'm going to break the hydrogen-oxygen bond. I believe that's it. And then I'm going to make a carbon-carbon single bond, a carbon-oxygen bond, and one carbon-hydrogen bond. I'll do that on this one. So that's how I can take these two pieces and make it into this. So I'm basically breaking this apart and breaking this apart. Then I'm rejoining these two fragments with a single bond. I'm adding a hydrogen over to here, and I'm adding the OH group over to here. So if I look at my values then, okay, for breaking, for my positive, I'm breaking this double bond. I have plus 611. And I'm breaking a hydrogen-oxygen bond. That's 464. For the negatives, I'm making a carbon-hydrogen bond. That's negative 414. I'm making a carbon-carbon single bond. That's negative 347. And I'm making a carbon-oxygen bond, a negative 360. Okay, so if I add all of this together, then the total that I end up with is what I would have for the total reaction. So 611 plus 464 minus 414 minus 347. So the total on this ends up being an enthalpy for the reaction of negative 46 kilojoules per mole of reaction. Now I want to talk about enthalpy and Q, what the similarities are between them and what the differences are. And this is something that's very underrated for new people into chemistry. So if you're struggling, how to figure out whether something's exo or endothermic or positive or negative, this is the problem that you're having. So enthalpy, you want to think of as every single type of energy within a system of chemicals. So I have a pile of chemicals, it's every potential or kinetic energy within that pile. So all of the bond energies, the intermolecular force energies, all of the kinetic energy of their motions, all of the nuclear energies, every single type of energy that that thing contains is what the enthalpy is. And that's nearly impossible to figure out. So instead what we do is we manipulate them and change them, and we look for how the enthalpy changes by what happens to the surroundings. Okay? So that brings us into heat. Now heat is, when we do a chemical or physical process, there's going to be a heat exchange with the surroundings. And so we want to be very explicit at the beginning that when we talk about enthalpy, we are referring to the chemical system that we're looking at. So if we're doing a chemical reaction, we're talking about the enthalpy of those chemicals. Whereas when we're looking at the heat, often we're looking at everything around those. Okay, so if you do a chemical reaction in solution, the water is your surroundings, the chemicals in that water is what your enthalpy is describing. Okay, and there's a lot of struggle with that because we don't point that out well. A lot of people will say that enthalpy is heat. Now numerically they're the same in most situations because the change in energy of the chemicals is equivalent to how much energy the surroundings will gain. But the directionality is usually the opposite. So usually whatever this is the opposite in sign. If your enthalpy change is negative, then you're gaining energy for the surroundings. If your enthalpy change is positive, you're losing energy for the surroundings. So a good example of that is usually I see people struggle with the difference between fire. And usually we start off and we say that fire is exothermic, its enthalpy is negative, and that makes sense to kids and they start to associate fire with exothermic. But then when we talk about melting ice, all of a sudden things start to go awry when we say that that's endothermic. Because to a student, they think warm, exothermic, warm, endothermic, and then it doesn't make sense. And what needs to be really explicit is that here we are talking about the chemicals burning, that chemical reaction is losing energy to me. I feel warm because of that energy exchange, but the chemicals are losing the energy. Whereas the ice, maybe I'm warm and holding this ice and that's what's causing it to melt, but the ice itself is picking up the energy. And so what I'm looking at in this case is the ice, and in this one it's my chemical mixture. And those are undergoing opposite processes. If we start to point out every single time that the enthalpy refers to the set of chemicals, that becomes a lot easier to analyze whether it's negative or positive. Okay, so from there then, you're on a test and you're asked to find delta H on the test. There are 4 different things you can see. So number 1, if you're given a lab style question, and specifically usually it's going to be a calorimetry where you're given some kind of MCAT calculation. You're given a mass of water, a temperature change, and then you can go ahead and take Q divided by the number of moles of chemical reactant, and that will give you your enthalpy. Okay? So if you're dealing with a lab experiment, or if you're given a question that looks like a lab experiment, that's probably how you're going to find enthalpy. If you're just given a reaction, so 2A plus B becomes 3C plus D. As I say, find the enthalpy. Well, there's not much to work with here. Then you're going to have to look up table values for enthalpy of formations to figure out what the enthalpy of formations of those 4 things are, sum up the products, sum up the reactants, and then subtract products minus reactants to get your enthalpy change. If you're given a set of reactions, like 3 to 5 reactions, then you're looking at a Hess's law. Now you're looking at a situation where you're going to have one that you don't know the enthalpy for and the others you do. And you're going to have to piece together the ones you do to form the one that you don't, and then add up the enthalpies. And then the 4th thing, you'll get a reaction that looks like a number 2, but it'll be something where it's structural formulas. It'll be Lewis structures where you can see the bonds, which bonds you're going to break and make, or some kind of simple organic reaction where there's clearly a rearrangement of bonding, and then you would use your bond energies to solve for that. So those are the different things you will see where you will have to calculate delta H, and hopefully that will help set you up. Now this one is the one that people struggle with the most. People recognize Hess's law. Sometimes this is a little bit of trouble, but this was the one that causes people the most grief, and so going in knowing that those are the only 4 ways you can solve for enthalpy is usually quite a bit of help for this particular one.